So here we've got data which was recorded from our lab, and what we've got here is, this is our W prime. So we've collected data at 120, 110, we've done a VO2 max trial, and we've done a 94% VO2 max trial here. If you want to watch this being recorded, you can go to my YouTube channel, which is Exercise Physiology Made Simple, and you'll see the actual data collection that was undertaken here. So this is the asymptote. The W prime gives us the curvature constant, and each of these areas reflects that W prime for the participant. So the question is, how did I actually calculate this? Because I can't just look at the curve and estimate it. I have to be able to calculate this critical power and actually work out what the size of the W prime is. Well, this is how we do it. So this looks pretty similar. Again, the same thing's been done. We've kind of got the critical power there. We haven't shown you how you've got to it. We've got trials 1, 2, 3, 4. We've got the area. So we know this is calculated the asymptote. So how do we get to this asymptote of the curve? Well, it's actually much easier than one would think. You simply do what is called a linear P model. This is the easiest of all the models that exist. There are other models that are out there, but particularly if you're working with coaches, you're working with athletes, or you just want to be actually efficient, this is a really easy model to use. Rather than plotting what you've got here, which is time versus power, you now plot the inverse of time, 1 divided by time. And what you'll find is this. Look at the way the curve is plotted here to the way this line occurs here. And if you take a hyperbolic and you plot the 1 against time, or sorry, work out the inverse of time, you'll always end up with this linear relationship. That is, the inverse of time for trial 1 has the greatest inverse of time, trial 4 has the shortest inverse of time, whereas, oops, we go back, whereas fundamentally, trial 4 is the trial that has the longest time. But what it does is it allows us to take a linear response. The intercept of that relationship on the y-axis gives you the critical power. The gradient of the slope of the line is the W prime. So you've now got two amazing parameters. I've got the boundary between heavy and severe exercise, and I've got this W prime, which is fundamentally this anaerobic capability of the individual, both of which are trainable, both of which respond both clinically and athletically. And so let's take this a little bit further and just have a look at this kind of relationship to other variables. So what you've got here, you've got the asymptote of the power curve, that's critical power on the y-axis in panel A. And what they've done is they've plotted this against critical power, against VO2 max, apologies, it is critical power, against VO2 max. And you can see that there is a pretty good relationship between the two. In other words, the higher the critical power, the higher the VO2 max. And the same also applies for the W prime. So it shows you really how aerobically linked the critical power is, but also how aerobically linked one's W prime is. Although W prime represents this kind of anaerobic capability, that curvature constant represents that kind of anaerobic capability, it's not surprising it's in the severe domain. It's going to have a large aerobic contribution to it. So you should expect to get this relationship between the two. So individuals who've got COPD will have a very low VO2 max. They, by definition, as we saw right at the start of this presentation, have a very low critical power. Now, I mentioned right at the beginning that this offers you far more than respiratory compensation point and MLS will do in terms of identifying the boundary between heavy and severe. Yes, I can track it, and I could track those, but you can do so much more with this. So what I've done is I've taken that data, which is the data from Hill that we saw earlier on, and I've just put these stars on here just to show that these are just workloads that one would have maybe completed across this. But now what we're going to do is going to show you how the understanding of critical power and W prime can be used to actually make some really important calculations. Once you know critical power and you know W prime, you can work out the time to exhaustion at any severe work rate. So that's T lim equals the W prime divided by the power minus the critical power. I can then work out an exhaustion at a set time. So the power equals the W prime divided by the T lim plus the critical power. I can actually now work out the performance time for a fixed amount of work. So T lim will equal the wattage or the power minus the W prime divided by the critical power. In other words, I can now prescribe exercise based upon critical power. Now, if I'm thinking about that in terms of performance, I can use that to establish pace. If I'm thinking about that in setting, for example, high intensity interval training, which is training that really starts at the critical power and goes up to about 120% VO2 max, I can start to prescribe it from that perspective as well. So it opens up a huge numbers of opportunities for us. So not only does it give us an indication of the bioenergetics of the tissue, it really opens up a lot in terms of our ability to prescribe training, to monitor athletes, to monitor clinical populations. The final thing I want to leave you with is this, and it is a food for thought, is one of the primary criticisms of critical power is it is time consuming. Even if you go with that data, which was from Carsten's group, which was, well, look, I do these trials, but I separate them by 3 hours. If I'm doing 4 trials, I've got a really long day with an athlete. There's a lot of issues with that. So one of the things that was proposed by Annie van Hattelaar and colleagues was, well, can you do this in one sitting? And they proposed what was called the 3-minute all-out cycling test. I'm not saying this is the perfect answer because I think there are huge limitations to this, but I thought I would show you this because it may offer some insight. So what happens here? Well, the subjects are asked to increase their cadence to approximately 110 revs during the last 5 seconds of the baseline period. The resistance on the pedals during the 3-minute effort was set using the linear mode of the ergometer so that the subjects would attain the power output halfway between VO2 peak and gas exchange threshold. And what they do is they go for as hard as they can, and they're going basically on that power for 3 minutes. And what they found is where this line levels out, you see you get this hyperbolic, it starts to level out, and they argued that this asymptote was the critical power. And it does seem to tally very, very well to the linear P model that I showed you earlier on. The problem with it is purgatory. It is horrible. So if you've ever done an MAOD test, which is about 2 minutes, this makes that look like kids play. If you've done a McArdle all-out test, which is a 2-minute test, this is getting close to that. That's 2 minutes against a constant workload of about 5.6 kilos on a cycle ergometer. It's akin to that. It's horrible, but you have to maintain the cadence. It's an awful test to go through. So I think the efficacy of this, you couldn't use this clinically. And I think athletes really don't like it. So although critical power has got its limitations, and although this does seem to be a way around it, I think the efficacy of this is quite limited.